Hello and welcome to General Astronomy Lecture 20, Why the Sun Shines. Astronomy today encompasses the study of the entire universe, but the root of the word astronomy comes from the Greek word for star. At this point in our course, we will turn our attention to the study of the stars, the namesake of astronomy. When we think of stars, we usually think of the beautiful points of light visible on a clear night. But the nearest and most easily studied star is visible only in the daytime, our sun. In this lecture, and the next, we will study the sun in some detail. We will see how the sun generates the energy that supports life on Earth. Equally important, we will study our sun as a star so that it can serve as an introduction to the study of stars throughout the entire universe. The sun is the largest member of the solar system. It has 1,000 times more mass than all of the planets, moons, asteroids, comets, and meteoroids put together. It is also a remarkably typical star, with a mass, a size, a surface temperature, and a chemical composition that are roughly midway between the extremes exhibited by the myriad of other stars in the heavens. As we have learned in the previous lectures, the sun's spectrum is close to that of an idealized black body with a temperature of 5,800 degrees Kelvin. Thanks to this high temperature, each square meter of the sun's surface emits a tremendous amount of radiation, principally at visible wavelengths. The total amount of energy emitted by the sun each second, called its luminosity, is about 3.9 times 10 to the 26 watts. That is 3.9 times 10 to the 26 joules of energy emitted every second. Astronomers denote the sun's luminosity by the symbol L with a circle and a dot in the subscript. That is common for all solar quantities, so whenever we're talking about the sun, you'll see some letter for the quantity, in this case luminosity, with that symbol below. So if you ever see that circle with a dot, you know we're talking about the sun. So suppose that you stood in a room that contained an object at the same temperature as the sun, but was with only a surface area of 1 square millimeter. Do you think it would burn you? Well, the answer is, surprisingly maybe for some people, no. Such an object would emit around 100 watts, similar to a household light bulb. Just like a light bulb, you would have to put your hand quite close to feel any warmth. What helps make the sun so strong is that each square meter patch of the solar surface emits about as much as 1,000,000 100-watt light bulbs, and the sun's surface has more than 1,000,000 trillion of those 1 square meter patches. Taken together, it is the high temperature and the large size of the sun that makes it so bright. So it's really quite remarkable. So you need that combination of temperature and size to give off this immense luminosity. So even though something can be as hot as the sun in the room, if it's really, really small, it's not going to burn you. But because the sun is both tremendous in size and temperature, it's quite impressive. The sun's energy is vital to human existence. Ancient peoples certainly recognized that fact. Some worship the sun as a god. Others created mythologies to explain its daily rise and set. But no one who lived before the 20th century knew the energy source for the sun's light and heat. Here, we ask a few basic questions. What keeps the sun's visible surface so hot? What is the fundamental source of the tremendous energy that the sun radiates into space? And also, what source of energy could have kept the sun shining for so long, that is, 4.5 billion years? Well, most ancient thinkers imagined the sun to be some type of fire, perhaps a lump of burning coal or wood, since that's all we really could reference back in the day. It was a reasonable suggestion for these times, since the idea could not be tested. Ancient people did not know the size or distance of the sun, so they could not imagine how incredible its energy output really was. Nor did they know how long Earth had existed, so they had no way to realize that the sun had provided this light and heat for a very long time. Modern scientists, however, began to address the questions of how the sun shines around the middle of the 19th century, by which time the sun's size and distance has been measured with reasonable accuracy. The ancient idea of the sun being fueled by burning coal or wood was quickly ruled out. calculations showed that such burning could not possibly account for the sun's huge output of energy. Other ideas based on chemical processes were likewise ruled out. Now, back in the day, they weren't able to prove that burning was or was not the source of energy for the sun, but we can prove that it's not the source now. So I'm actually going to show you a little bit of how this works. So let's prove that burning could not work in just a few simple steps, relatively speaking. On Earth, a common way to produce heat and light is by burning fuel, such as a log in a fireplace or charcoal in a barbecue grill. This process does not explain the energy released by the sun, since this process could not continue long enough for a long enough time to explain the age of the Earth. It might seem difficult to estimate how long the sun could last if its energy came from burning, but the calculation only requires a few simple steps. Now, I'm going to throw some numbers at you. I'm not going to necessarily derive all of these numbers, but these are research numbers that I'm using here. The chemical reactions involved in burning releases roughly 10 to the minus 19 joules of energy for every atom. Therefore, the number of atoms that would have to undergo chemical reactions each second to generate the sun's luminosity of 3.9 times 10 to the 26 joules per second is roughly, take that at joules per second and divide by how much energy is released per atom. When you do that, you'll find out that 3.9 times 10 to the 45 atoms per second are being used up. So let's see what happens then. So we're using that many atoms per second. Well, from its mass and chemical composition, we know that the sun contains 10 to the 57 atoms. So we're using basically 4 times 10 to the 45 per second, but the sun in total contains about 10 to the 57. Thus, the length of time that would be required to consume the entire sun by burning is just those two numbers divided, and that would give you roughly 10,000 years in time. Clearly, this can't be the case, right? Because this period of time is far shorter than the known age of the Earth. So chemical reactions cannot explain how the sun shines. So in just a few steps, with a couple numbers given, of course, we were able to prove that burning could not sustain the sun for as long as it's been around. That is 4.5 billion years. Burning roughly would only last about 10,000 years before it runs out of that fuel. In the mid-1800s, scientists argued that the tremendous weight of the sun's outer layers should cause the sun to contract gradually, compressing the interior gases. Whenever a gas is compressed, its temperature rises. So what I have here on the right in this image is what we call a fire syringe. It's just this little chamber where you put a small piece of paper inside and you push down on that piston like you see this guy doing. And as you do that, it's just air and a piece of paper inside, and the paper will catch on fire. So I will link this video in the description on YouTube. So it's a good point, I would say, to go watch that video. It's just a really fascinating video. I think it's only a minute or two long. But it shows one of these things in use. So it's a good video to watch. Go take a look at that, and then we can return to the lecture. It was therefore suggested that this contraction could cause the sun's gases to become hot enough to radiate energy out into space. Right? So if you compress a gas and it heats up, like we know here on Earth, well, why can't that be a source of energy for the sun? This process, which is called the Kelvin-Helmholtz contraction, actually does occur during the early stages of the birth of a star like the sun. But a shrinking gas cloud heats up because the gravitational potential energy of gas particles from the cloud's center is converted into thermal energy as the gas moves inward. But does it explain the sun's energy today? Kelvin-Helmholtz contraction cannot be the major source of the sun's energy today. If it were, the sun would have had to be much larger in the relatively recent past, right? If it's continually contracting, we should have seen it being larger in the past in that case. Helmholtz's own calculations showed that the sun could have started its initial collapse from the solar nebula no more than about 25 million years ago. Any more, and it would have burned out by now. Hence, because we know Earth to be much older than 25 million years, this model of a sun that shines because it shrinks cannot be correct. So although this contraction does happen at some point in the sun's life, it is not the energy source for the sun that we see today. So just like burning, neither of them could have lasted long enough to sustain the sun for as long as it's been around. So then what is the source? Well, with both chemical processes and gravitational contraction ruled out as possible explanations for why the sun shines, scientists were at a loss. There was no known way that an object the size of the sun could generate so much energy for billions of years. A completely new type of explanation was needed, and it came with Einstein's publication of his special theory of relativity in 1905. According to Einstein's special theory of relativity, a quantity m of mass in kilograms can, in principle, be converted into energy, given by the symbol E, in joules, according to the now famous equation E is equal to mc squared, where again c is the speed of light. So this is really, really amazing. A small amount of matter can release an incredible amount of energy. This is literally showing that mass can be converted into energy. And this is a huge breakthrough, especially for astronomy. So it's insane that how much energy can be released by a small amount of mass. Here's just an actual example of this. If the mass in just one penny, which is about 2.5 grams, were completely converted into energy, it would release about 5 times the energy of the nuclear bomb detonated over Hiroshima. Calculations immediately showed that the sun's mass contained more than enough energy to account for billions of years of sunshine, if the sun could convert the energy of mass into thermal energy. Inspired by Einstein's ideas, astronomers began to wonder if the sun's energy output might come from the conversion of matter into energy. In the 1920s, the British astronomer Arthur Eddington showed that temperatures near the center of the sun must be so high that atoms become completely ionized. Now, we're getting into some technical things here for a bit, but ionization is the process by which an atom or a molecule acquires a negative or positive charge by either gaining or losing electrons to form what we call ions. So this often comes with other chemical changes as well. We don't really have the time to go through all of the chemistries and small, topics in physics here. So if you want to learn about ionization, you can look it up a bit more, but there's really just not enough time. But the point is, it's hot enough to ionize these atoms. So hence, at the sun's center, we can expect to find hydrogen nuclei and electrons flying around independent of one another. Right, so it's hot enough to where they can ionize, meaning you gain or lose these electrons, so you can find them flying around on their own. So British astronomer Robert Atkinson suggested that under these conditions, hydrogen nuclei could fuse together to produce helium nuclei in a nuclear reaction that transforms tiny amounts of mass into large amounts of energy. The fusing together of nuclei is called thermonuclear reactions, or fusion, since it can take place only at extremely high temperatures. Fusion occurs within the sun because the 15 million degree Kelvin plasma in the solar center is like a soup of hot gas, with bare, positively charged atomic nuclei and negatively charged electrons, whizzing around at extremely high speeds. At any one time, some of these nuclei are on high-speed collision courses with each other. In most cases, electromagnetic forces deflect the nuclei, preventing actual collisions, because positive charges repel one another. But if nuclei collide with sufficient enough energy, they can stick together to form a heavier nucleus. Sticking positively charged nuclei together is not easy. The strong force, which binds protons and neutrons together in atomic nuclei, is the only force in nature that can overcome the electromagnetic repulsion between two charged nuclei. In contrast to gravitational and electromagnetic forces, which drop off gradually as the distance between particles increases, the strong force is more like glue or Velcro. It overpowers the electromagnetic force over a small distance, but is insignificant when the distance between the particles exceeds a typical size of atomic nuclei. The key to nuclear fusion, therefore, is to push the positively charged nuclei close enough together for the strong force to outmuscle the repulsion that they experience because they're both positively charged. This high pressure and temperature in the solar core are just right for fusion of hydrogen nuclei into helium nuclei. The high temperature is important because the nuclei must collide at very high speeds if they are to come close enough together to fuse. The higher the temperature, the harder the collisions, making fusion reactions more likely. The high pressure of the overlying layers is necessary because without it, the hot plasma of the solar core would simply explode into space and shut off the nuclear reactions. So let's investigate the fusion process in the Sun in a little bit more detail. So in the next few slides, several slides, we're going to learn about the proton-proton chain with the lovely abbreviation, the PP chain. Hydrogen nuclei are simply individual protons, while the most common form of helium consists of 2 protons and 2 neutrons, as you can see in this image. The overall hydrogen fusion reaction therefore transforms 4 individual protons, like you see here, into a helium nucleus containing 2 protons and 2 neutrons. So the overall reaction is 4 hydrogen is converted into helium, and it gives off a little bit of energy. So this overall reaction actually proceeds through several steps involving just 2 nuclei at a time. The sequence of the steps is again what we call the proton-proton chain, since it involves collisions between protons, the hydrogen nuclei. So let's look at each step of this proton-proton chain, something that is very important and you'll probably want to follow along with. Step 1. 2 protons, that is 2 hydrogen atoms, fuse to form a nucleus consisting of 1 proton and 1 neutron, which happens to be a form of hydrogen known as deuterium. Note that this step converts a proton into a neutron, reducing the total nuclear charge from +2 to 2 fusing protons to +1 for the resulting deuterium nucleus. So each of these has a positive charge, but in the reaction, one of them is converted into a neutron. So you're losing some of that positive charge. The lost positive charge is carried off by what we call a positron or a anti-electron. We won't go into what those are. The antimatter version of this electron with a positive rather than negative charge. A neutrino, which is a subatomic particle with a very tiny mass, is also produced in this step. Note, though, that the positron won't last long because it soon meets up with an ordinary electron, resulting in the creation of 2 gamma-ray photons through matter-antimatter annihilation. So lots of fancy words here. Really, all you have to worry about is the fact that it's 2 protons coming together to form deuterium. The extra stuff doesn't really matter for our course. Now, this step must occur twice in the overall reaction since it requires a total of 4 protons. So this happens twice. You get 2 protons come together to form deuterium, and you have that happen again. That is the first step. 2 protons come together and form deuterium. Step 2. A fair number of those deuterium nuclei are always present along with the protons and other nuclei in the solar core. So even though we made some deuterium, there's still protons and other things floating around. Since step 1 occurs so infrequently, right? So it happens so frequently, that it happens about 10 to the 38 times per second. That's 10 followed by 38 zeros. That's how many times deuterium is created every second. Step 2 occurs when one of these deuterium nuclei collides to fuse with a proton. So here is our deuterium now that we made in the last step. Well, now it's going to collide with one of those free protons. The result is a nucleus of helium-3, a rare form of helium with 2 protons and 1 neutron, along with a gamma-ray photon. This step also occurs twice in the reaction. So, in the first step, we make deuterium, then that deuterium collides with another proton to give us helium-3. The third step and the final step of the proton-proton chain requires the addition of 1 more neutron to the helium-3. So, thereby making normal helium-4, So, the final step can proceed in several different ways, but the most common is through a collision of 2 helium-3 nuclei. So in the last step, step 2, we made a couple helium-3s. Well, now those helium-3s collide, and what happens is each of these come together to give us helium-4. So in the process, 2 of the protons are lost, so they kind of recycle and go back into the star, but then we finally have made our helium. Notice that a total of 6 protons enter the reaction during steps 1 and 2, right? So let's go back for a second. In step 1, we gain 4 protons coming together to do this. And then we also add in 2 more protons to do this. So it's a total of 6 protons that are coming together. 2 come back out though, right? So 4 come together, but in step 3, we lose 2 of them back into the sun. So the overall result is that we use 4 protons to make helium. So the gamma rays and subatomic particles carry off the energy released in the reaction. So all these guys here, the gamma ray photons and everything, they give off the energy. So this is the proton-proton chain, converting 4 protons into a helium atom. And it occurs in those 3 steps that we talked about. So it's good to look back through them and try to make sure you can understand this. And if you're in my course, I actually believe you have a homework problem to explain this process in general. Well, fusion of hydrogen into helium does generate energy because a helium nucleus has a mass that is slightly less, that is about 0.7% less, than the combined mass of those 4 hydrogen nuclei. That is, when 4 hydrogen nuclei fuse into helium nucleus, a little bit of mass disappears. This disappearing mass is what becomes energy in accordance with Einstein's formula E = mc squared. About 98% of the energy emerges as kinetic energy of the resulting helium nucleus and radiative energy of the gamma rays that are lost. As we will see, the energy slowly percolates to the solar surface, eventually emerging as the sunlight that bathes Earth. Neutrinos carry off the other 2% of the energy. Overall, fusion in the sun converts about 600 million tons of hydrogen into 596 million tons of helium every single second, which means that 4 million tons of matter is turned into energy every second in the sun. Although this sounds like a lot, it is a minuscule fraction of the sun's total mass and does not affect the overall mass of the sun in any measurable way. Luckily, the sun's core contains enough hydrogen to have been giving off energy at the present rate for as long as the solar system has existed, about 4.5 billion years, and to continue doing so for far more than 6 billion years into the future. So here's a quick calculation check for you. Try to use that Einstein equation and figure out how much energy is released when 5 kilograms of mass is converted into energy. So take a minute to work that out and return when you are ready. All right, well, according to Einstein's equation that E = mc squared, a mass of 5 kilograms is equivalent to 5, so plug this in, so plug in 5 kilograms for m, and plug in c, the speed of light, 3 times 10 to the 8 meters per second, and when you calculate that, you should get 45 times 10 to the 16, or 4.5 times 10 to the 17 joules. So this is equivalent to burning about 100,000 metric tons of coal. So just a 5 kilogram mass, if converted into pure energy, would be the equivalent of 100,000 metric tons of coal burning. Very impressive. And I have one more. This one's a concept check. How do you suspect that astronomers estimate that our sun can continue to shine for more than 6 billion years? In other words, how do we know it's going to last that long? Take a minute to think about it and return when ready. Okay, well, we know how much energy the sun is outputting right now, and we also know how much fuel is in there. So we can use the current energy output of the sun to estimate how fast the sun is consuming its usable fuel. Then, the amount of hydrogen fuel remaining in the sun's core indicates how much longer the sun will shine. So it's really about as simple as that. It's kind of like your gas tank in your car. We know roughly the miles per gallon that a car has and how many gallons we have in our tank. Thus, we could, if we wanted to, calculate or estimate about how long we can drive before we run out of gas. Same exact thing here with the sun. All right, so we're going to start talking a little bit about the internal workings of the sun, which will transition us into our next topic in the next video, which is the structure of the sun. The sun is not undergoing any dramatic changes. It is not suddenly expanding or contracting. This is because the sun has achieved a balance, which is known as hydrostatic equilibrium, or you'll sometimes hear me say gravitational equilibrium, between the outward push of the internal gas pressure and the inward pull of gravity. The outward push against gravity comes from the internal gas pressure as energy radiates outward from the nuclear reactions in the core. So you've got all these nuclear reactions, hydrogen being converted into helium in the core. That releases energy outward. The sun's internal pressure precisely balances the gravity at every point within it, thereby keeping the sun stable in size. So even though we have energy radiating outward and gravity pulling inward, they do so at about the same rate everywhere, so the sun doesn't contract because of gravity or just explode because of all that energy. A human pyramid provides a simple example of this gravitational equilibrium. The bottom people support the weight of everybody above them, so their arms must push upward with enough pressure to support all of this weight. At each higher level, the overlying weight is less, so it's a little easier for each additional person to hold up the rest of the stack. Gravitational equilibrium works much the same way in the sun, except the outward push against gravity comes from the internal gas pressure rather than the people's arms. The sun's internal pressure precisely balances the gravity at every point, and again, that is why the sun remains stable in size pretty much throughout its life, for the most part. We'll see some changes soon when we talk about the lives of stars. So not only is it in a hydrostatic equilibrium, but another balance sustained by the sun is known as thermal equilibrium, which states that while the temperature in the solar interior is different at different depths, the temperature at each particular depth remains constant in time. So it might be hotter near the core and cooler near the surface, but at each certain depth, say, 100 meters into the surface or 1,000 meters into the surface, everywhere at 1,000 meters around the sun, it's roughly the same temperature and it stays that way. For the sun to be in thermal equilibrium, all the energy generated by thermonuclear reactions in the sun's core must be transported to the sun's glowing surface, where it can be radiated into space. If too much energy flowed from the core to the surface to be radiated away, the sun's interior would cool down. Right? So if it was being radiated away really fast, well then it would cool off. And alternatively, the sun's interior would heat up if too little energy flowed from the surface. So maybe it's producing a bunch of energy in the center, but something's causing the energy to be kind of trapped. Well, then it's going to heat up. So there is some kind of equilibrium allowing it to radiate away as quickly as it's made, essentially. So let's look at this energy transport, how the energy is transported through the sun. This is very important. So we have something called the solar thermostat. It balances the sun's fusion rate so that the amount of nuclear energy generated in the core equals the amount of energy radiated away from the surface as sunlight. However, the journey of solar energy from the core to the photosphere, that is the surface of the sun, takes hundreds of thousands of years. Most of the energy released by fusion starts its journey out of the solar core in the form of photons, those little packets of energy of light. Although photons travel at the speed of light, the path that they take through the sun's interior zigzags so much that it takes them a very long time to make any outward progress. So these things are moving at the speed of light, the fastest known speed for anything to move, but it still takes them an enormously long time to get out of the sun. Deep in the solar interior, the plasma is so dense that a photon can travel only a fraction of a millimeter in any one direction before it interacts with an electron. Each time a photon collides with one of these electrons, the photon gets deflected in a new and random direction. The photon therefore bounces around the dense interior in a haphazard way, sometimes called a random walk, and only very gradually works its way outward from the sun's center. The technical term for this slow outward migration of photons is radiative diffusion. To diffuse means to spread out, and radiative refers to the photons of light, or radiation. So thus we have something called the solar thermostat. Nuclear fusion is the source of all the energy the sun releases into space. If the fusion rate varied, so would the sun's energy output, and the large variations in the sun's luminosity would almost surely be lethal to life on Earth. Fortunately, the sun fuses hydrogen at a steady rate, thanks to the natural feedback process that acts as a thermostat for the sun's interior. To see how it works, let's examine what would happen if a small change were to occur in the core temperature. So let's suppose this is basically a symmetric image. The left side shows what happens if you have a drop in temperature. The right side shows what happens if you have a rise. So let's take a look at what happens if the temperature were to rise very slightly. So let's look at the right side of this figure. Well, if you slightly increase the temperature, the rate of nuclear fusion is extremely sensitive to temperature. So a slight temperature increase would cause the fusion rate to soar, as protons in the core collide more frequently with more energy. Because energy moves slowly through the sun's interior, this extra energy would be bottled up inside the core, temporarily forcing the sun out of energy balance and raising the core pressure. The push of this outward pressure would temporarily exceed the pull of gravity, causing the core to expand, but then cool. This cooling, in turn, would cause the fusion rate to drop back down until the core returned to its original size and temperature, restoring both the gravitational equilibrium and the energy balance. Now, the opposite is also true. A slight drop in the sun's core temperature would trigger the opposite chain of events. The reduced core temperature would lead to a decrease in the rate of nuclear fusion, which then causes a drop in the outward pressure and a contraction of the core because gravity will start to take over. As the core shrank, its temperature would rise until the fusion rate returned to normal and restored the core back to its original size and temperature. So no matter what, effectively, either way, if you have a slight increase or decrease in temperature, there's this thermostat process where the core might expand or contract and then cool or heat up as a result. And the effect is that you just keep returning to what is considered normal. So let's take a look at one last thing before we shift to our next lecture on the sun. While the processes involved in gravitational equilibrium prevent erratic changes in the fusion rate, they also ensure that the fusion rate gradually rises over billions of years. This rise in the fusion rate explains the gradual brightening of the sun with time. Remember that each fusion reaction converts 4 hydrogen nuclei into 1 helium. The total number of independent particles in the solar core is therefore gradually decreasing with time, right? Because we're using 4 things to make 1. So we have less and less material in the center. This gradual reduction in the number of particles causes the solar core to shrink. This slow shrinkage, in turn, gradually increases that core temperature and the fusion rate, keeping the core pressure high enough to counteract the stronger compression of gravity. Therefore, models indicate that the sun's core temperature should have increased enough to raise its fusion rate and luminosity by about 30% since the sun was born 4.5 billion years ago. This increased output of energy causes an expansion of the sun's outer layers, and so its size has also been gradually increasing. So you can kind of see that in the image at the top. The sun today is a little bit bigger than it was when it was formed, and it's a little bit brighter. So in summary, to answer the question, why does the sun shine? That is the title of this lecture. It is that about 4.5 billion years ago, gravitational contraction made the sun hot enough to sustain nuclear fusion in its core. Ever since, energy liberated by fusion has maintained gravitational equilibrium and energy balance within the sun, keeping it shining steadily and supplying the light and heat that sustain life on Earth. Calculations show that the sun was born with enough hydrogen in its core to shine steadily and maintain its gravitational equilibrium for about 10 billion years. The sun is therefore only about halfway through its 10 billion year lifetime. About 5 billion years from now, when the sun finally exhausts its nuclear fuel, gravitational contraction of the core will begin once again. Some of the most important and spectacular processes in astronomy arise from the changes that occur as the crush of gravity begins to overcome a star's internal source of pressure. And that is a topic that we will get into in several lectures from now when we talk about the deaths of stars. But for now, this is a good point to stop. In the next video, we are going to transition into talking about the structure of the sun. So we'll look at the interior quote-unquote layers and the sun's quote-unquote atmosphere as well. So have a great day, and I'll see you in the next video.